This is a story that begins in the late 1980s with an observation that was at first difficult to understand, but once explained, produced an unexpected opportunity and an exciting 10-year journey that one could not have possibly imagined at the outset. For this, I have to acknowledge the individuals shown at the bottom of the slide, as well as Cygnus and the NIH who funded the research. My laboratory then was at the University of California, San Francisco, and we were investigating methods to enhance the delivery of drugs into and through the skin. Peretz Glickenfeld had arrived on sabbatical, and he convinced me to begin a project on iontophoresis, the principle of which is shown in the top figure of this slide. That is, the movement of charged drugs across the skin can be significantly enhanced by the imposition of an electric field. Positively charged species are repelled from the anode when the circuit is activated, resulting in a significantly higher flux than that possible by passive diffusion. By controlling the small current applied, drug delivery can be controlled at a constant rate with constant current, or made pulsatile by turning the current on and off. The data in the two other graphs illustrate these opportunities for a 1000 Dalton peptide and for a drug to treat migraine. Peretz's first objective was to design an in vitro diffusion cell that would mimic the use of iontophoresis in vivo, i.e. where both electrodes would be in contact with the surface of the skin. The solution is shown in the simple diagram on the bottom left of the slide, and more elegantly drawn in the larger figures to the right, taken from our patents. The trick was to create anode and cathode chambers physically and electrically isolated from one another at the surface of the skin, but with a common receptor phase. The current path in the circuit, therefore, travelled between the electrodes by crossing the skin twice. After some heroic glass blowing work, we had a prototype to test, and it worked successfully, duplicating previous results acquired with conventional cells. There was just one problem. We found that there was always, at the end of the experiment, a measurable amount of the drug delivered from the anode that was recovered in the cathode compartment. The drug obviously was positively charged. We were pretty sure that this was due to a leak across the skin surface, but we could never find any proof. So we designed a crazy experiment shown here using two cells, with one housing the anode on the left and the other the cathode on the right, and connected via their receptor chambers. Drug, in this case morphine delivery, was not affected by the design as shown in the graph, where the different symbols reflect the overlap of data from one and two cell experiments, and I can't remember which is which. In addition, the drug recovery at the cathode from the two-cell experiment was identical to that in the single-cell setup, and was not, therefore, due to an experimental artifact, such as a leak. It was clear then that morphine had been delivered across the skin from the anode, and had then been reverse iontophoretically extracted from the receptor phase into the cathode. With the clarity of hindsight, this was obvious, of course. Iontophoresis is a symmetrical process. And ions in the system, once the field is turned on, are moving across the skin in both directions under both electrodes. It's logical, therefore, that the technique can be used both for delivery and for extraction. A further factor to bear in mind was that the skin supports a net negative charge and is therefore perm-selective to positively charged ions, meaning that when an electric field is applied across it, there's an induced electroosmotic flow of solvent from anode to cathode that can also substantially increase the flux of uncharged polar water-soluble compounds as well. This got us thinking about possible applications of reverse iontophoretic extraction, and within a few nanoseconds, we simultaneously cried glucose. The next steps were self-evident. First, the very nice linear relationship of reverse iontophoretic extraction to subdermal concentration for common charged drugs was shown. Here I've illustrated that for clonidine and theophylline in the graph. Then we demonstrated that reverse iontophoretic extraction of glucose via electroosmosis also worked very well, with excellent proportionality. Look at table 1, the exact overlay of the ratios of the perfused concentrations and the amount sampled. And then look at table 2, the essentially constant extraction over time when glucose was held constant in terms of concentration in the receptor or in the subdermal compartment. By now, Girish Rao had joined the group. A license agreement for our intellectual property had been struck with the transdermal patch company Cygnus, and research funding provided to obtain in vivo proof of concept in healthy volunteers. This was achieved at UCSF, the reference at the bottom, and the technology was then transferred to Cygnus, who subsequently reported successful monitoring of glucose levels in periods of hyper and hypoglycemia in diabetic subjects. Look at those graphs on the left. The Clark error grid on the right shows the correlation between the reverse iontophoretically assessed glucose levels and the reference glucose concentrations determined by an independent analytical method. Almost all of the data fall in regions A and B, which are considered clinically acceptable. Cygnus was now in full-on development of a non-invasive glucose monitor based on reverse iontophoretic extraction. The device, the GlucoWatch Biographer, was approved by the FDA in 2000, and some of the clinical data supporting safety and efficacy are shown on this slide. Note the excellent tracking once again, and the impressive Clark-Ehret grid data once more on the right-hand side. There's over 2,000 individual data points there. Sadly, however, the story did not end well for the GlucoWatch or Cygnus. Despite the positive features highlighted in the green text shown on this slide, the device required a finger stick calibration before use and a long warm-up period. There was some mild to moderate skin redness observed in many users. You see those in the pictures. The device and the daily disposable element required, the photos in the top right, were expensive. After a short but valiant fight, Cygnus were forced to close, and the IP was acquired but not supported further, and the GlucoWatch soon became unavailable. However, all is not lost, and here in Bath, a refined approach to the GlucoWatch concept involving path-selective monitoring, specifically via hair follicles, has been pursued with some success, as shown on this slide. You can see how we built a miniature array platform to do that, and have successfully demonstrated that this works in man. Initial results and subsequent progress have been promising. So perhaps a miraculous resurrection of the concept may provide a sequel to the GlucoWatch story, but this time with a happy ending.